Okay, thank you everybody for joining us on this very, very warm day. I will hand over to Marcus.
So hello everyone, and it's my distinct pleasure to introduce Colin Snodgrass, who's the personal chair of planetary astronomy at the Royal Observatory at the University of Edinburgh. Colin got his master's degree from the University of St Andrews and moved on to Queen's University Belfast to finish his PhD in 2006. Went for Marie Curie to Göttingen, where I've met him first. And then he got a number of fellowships, the Rutherford Fellowship for the Open University, and moved to Edinburgh, where he has been ever since. Colin is an expert on solar system objects, comets, asteroids. And we talked today about how he reintroduced and brought back the Royal Observatory to its roots, and introducing a topic that has been there right from the start and was dormant for a while. So it's a great pleasure of having Colin over here, and he will talk about the interstellar visitors. So please take it.
All right. Thank you, Marcus. Thank you for the invitation to come and speak here. So today I'm going to tell you a little bit about this exciting new area of planetary astronomy, which is looking at planetary bodies that have come from other star systems. So the interstellar visitors, interstellar objects. And I'll start by talking about the first one of these that we discovered, which was called Oumuamua, which was discovered in 2017. And this caused a lot of excitement and a big stir. It's the first time that we've ever seen a macroscopic object that's come from another star system. They've been predicted for some time. I'll get on to what we thought we would see a little bit later. But this was picked up by the Pan-STARRS survey. It was actually discovered after it had passed by the Earth and passed by the Sun and was heading out of the solar system. It passed very close to Earth. In fact, this is why it was detected, because it came close enough to be bright enough to be picked up by these surveys. And as I said, it was already past us and disappearing away. So there was a very short period of time that this could be studied for. Basically a couple of weeks where it was, after the discovery was announced, where it remained bright enough to study with telescopes, and then it's been lost from view forever. So we had a very limited window to study it, but the world community of studying comets and asteroids jumped on this, and we had pretty much every telescope that you can imagine cancelling whatever it was doing and look at this instead. And the first thing to ask about it is, well, what is this thing? Is it some sort of comet? Is it some sort of asteroid? We'll ignore the more wild suggestions that went around. So to think about this first, what is the difference between a comet and an asteroid? So traditionally we thought of these as very distinct categories. You have comets, which are made of ice. They have very eccentric orbits around the sun. They show this activity. You get these beautiful tails. If you observe them from the ground, you see these long tails. If you send a spacecraft to them, you see a body that's outgassing. Whereas an asteroid is something that's made of rock. It has a nice circular orbit in the main belt. Doesn't show any activity. It just looks like a point of light. The name, asteroid, star-like. And so there's a nice clear distinctions. Recently, the field, you see that these are actually, we see now there's more of a kind of a continuum between the sort of rocky asteroids and the icy comets. There are a few things that blur the boundaries. The active asteroids, things in asteroidal orbits that show comet-like activity. There's a population of comets that orbit entirely within the main belt but are containing ice. There are things on cometary orbits that show no activity that we think are extinct. A couple of categories of things, dark comets or Manx comets. Manx comets for a comet without a tail, like the cats. So this is the, there are these things now that are somewhere in between, and we think there's a bit of a blur. But still, it's useful for us to think about which category we put things in, because it tells us a bit about composition, tells us a bit about formation. And so, first look at Oumuamua. It looks like an asteroid. This is a deep stacked image from a bunch of time with the Gemini telescope. And what you see is a point of light, no hint of a tail, no hint of a coma. And so maybe this is an interstellar asteroid. But this isn't the only way that we can think about what's the difference between a comet and asteroid. As well as the morphology, we can look at composition. And if we look at small bodies to get composition with spectroscopy, If you get a typical comet spectrum, what you see is you see emission bands. You see the gas in the coma fluorescing under the action of sunlight, and you see this is typical comet spectrum in sort of UV blue region. You see all of these emission bands, which is what gives a comet coma a kind of a blue-green glow in a photo. There's also emission features through the infrared and at pretty much every wavelength you can choose to observe. And if you look at an asteroid and get spectroscopy, what you see instead is you don't see emission features because there's no gas coming out of them. What you see are absorption features in a reflectance spectrum. So if you divide your observed spectrum through by a solar spectrum, you get some idea of what the composition is. You typically see these broad absorption features that are due to different mineralogy. The exact scales here aren't important, but the idea is you get different classes of asteroids depending on what their compositions are, based on these broad shapes. And so if we get a spectrum of Oumuamua, this is a spectrum that we acquired with the X-shooter instrument on the VLT, and also combined with ACAM on the Wilhelm Herschel telescope in La Palma. What you see is a fairly boring spectrum. It's got a red slope. There's no obvious absorption features, any strong clues on mineralogy. There's also no obvious emission bands, so there's no sign of outgassing here. This looks kind of like one of the sort of C or D type asteroids, and if you look in these classes, this kind of fairly featureless but red slopes, which are also what we typically see for if you look at the nuclei of comets, so the solid body in the middle. If you get just a reflectance spectrum from them, instead of emissions, you see this typically kind of featureless and red slope. So it looks kind of like a primitive type asteroid or a cometary nucleus. It's not necessarily giving us a good clue on its origin here, but it looks sort of like a body we'd expect to be icy. The other thing that we can typically do in small bodies to get some composition information from some point of light that we're not resolving is that we can measure a light curve, and we can look at how the brightness varies with time. And what causes brightness variations in small bodies is because these things tend to be non-spherical, and as they rotate, you get a different area projected, reflecting the sunlight back to you. That causes the brightness to go up and down in an unresolved image. And from this light curve, you can then measure how often it repeats and get an idea of how fast the thing's rotating. But you can also measure from the amplitude of the light curve some idea of how elongated it is, the shape of the body. And this is one of the early light curves published for Oumuamua. You can see that it shows this kind of double-peaked shape, typical of a small elongated body. But what's really worth noting here is the scale on the y-axis. From peak to trough here, this thing's changing by 2.5 magnitudes over a course of an hour or so. This is really a very a large elongation implied from that. If you look at what you need in just terms of difference in shape from the largest face to the smallest face to get 2.5 magnitude change, you're looking at an actual ratio of like 1 to 10. This thing must be really elongated to give you a light curve like that. And so for context, here's a distribution of sort of what you can get from asteroid light curves and how elongated those are in the solar system. One of the most elongated things there that has a shape model of Mark. This is asteroid 1865 Cerberus, and there's a low resolution shape model for that. You can see it's kind of really elongated shape. And then you've got Oumuamua, sort of off the scale at the end there, with a 1 to 10. And when this result came out, this lovely ESO press release image came out with it to highlight this thing's kind of weird, it's really elongated. And this definitely set off a bunch of the spacecraft people, because it does look a bit spaceshipy, and this was possibly a bad move. But it caused lots of excitement. And it is interesting, and it is a bit weird. But what were we expecting from a interstellar object, and how does this match? So we always knew that there must be interstellar objects out there. We always expected to find them. People have been predicting them for a very long time. Because we know the planet formation process is not 100% efficient at turning a disk of dust and gas into big planets and then keeping them in the system. In fact, it's very inefficient in this, and you've got lots of leftover little bits, which are our comets and asteroids. And then a lot of these are going to be scattered out of the system by gravitational interactions as the planets are forming, and then as the system's evolving through time. And you can get interstellar objects out of their parent system in one of two main ways. Either they have some gravitational slingshot around some planet, they have a close approach, and this kicks their orbit out to achieving an escape velocity. Or you can get things kind of lost from the edges of Oort clouds. So the Oort cloud is our comet cloud reaching halfway out to the edge of the next star. Things in the outer regions of that are very loosely bound to the sun. So it's relatively easy for a passing star to nudge them a bit and for them to lose their bound and go off wandering through space. But in either of these cases, if things are forming in the outer parts of disks and going on to be scattered out into Oort clouds or encountering giant planets as they're growing, these are things you find in the outer parts of disks. You expect that most of the material that's forming there is going to be more icy than rocky. And so the general expectation is that most interstellar objects, because they're going to come from the outer regions of their home systems, are going to be more ice-rich. They're going to be closer to comets. And so this is what you expect to see. You expect to see icy things, a bit like comets, as most of your interstellar objects. So can Oumuamua be an icy object like we expect? And its spectrum looks like, comet nucleus looks like a primitive asteroid that we now know a lot of these have water in them. But you would expect if you took an icy object like a D-type asteroid or a comet nucleus, and you brought it a quarter of an AU past close approach to the sun, like Oumuamua had, then it will light up like a comet, and you will have activity and you will have tails. And we didn't see that. So there's a bit of a puzzle. One of the possibilities that can help explain this, though, is that comets also have quite a low thermal inertia. It takes time for the heat of the sun to get to the inner layers. And this thing was going very fast past the sun. So in the same way that you can do, your baked Alaska where you heat the outside and you keep your ice cream inside, maybe you can do this with a comet. You can take it past the sun if it has an insulating layer. And we did some calculations for this in a paper in 2018 when we first looked at it. What sort of depth do you need to insulate to ices for it to not reach the sort of temperatures it needs for ices to sublimate in the few days it took to come past the sun and come past us? And actually, it's only tens of centimeters, which is well within the range that you expect there to be this kind of devolatilized layer where you've lost the ices over the time in interstellar space just due to bombardment by galactic cosmic rays and so on. The predictions there are centimeters to even a couple of meters depth that you would lose a lot of the ice. So it's entirely plausible that if you take a small body that's got this kind of insulating layer and it whizzes past the sun fast, that you don't actually get the activity until some later date when it reaches it. And in Oumuamua's case, it would have been way out of range for us to observe by the time that would have started. So it's possible that it can be an icy body and still come past the sun and not show activity. Can it be an icy body and have this weird shape? One of the things you can do if you have a spin rate and you have an idea of the elongation is you can just balance centrifugal and gravitational forces and say if this thing is a strengthless rubble pile, which we think is true for most small bodies, that they're held together just by self-gravity, not really any internal strength, you can figure out what density do you need just to hold it together with gravity. And the density you would need for Oumuamua's shape and rotation is higher than water ice, so it implies a more rocky body again. But that's using the assumption that these things are strengthless. And if you want to say actually it's made of water ice, you only need a few pascals of strength to hold this thing together. This is not a lot. A pile of talcum powder has a 10 pascal strength. So it doesn't require a lot of strength to explain it and still be an icy body. Comets, we think, are strengthless on a large scale. The rubble pile description works well. We know that when comet Shoemaker-Levy 9 went past Jupiter, gravity pulled it apart into multiple little comets, and modeling of that works perfectly well if you assume a completely strengthless body. But on a smaller scale, there is some strength there. This is an image at the top from Rosetta. There's this kilometer-high cliff on the on 67P. For that cliff to exist, there has to be some strength. These things are not entirely strengthless bodies that are just held with gravity. Doesn't need to be much, but it needs to be, you know, of order 10 pascals, enough to explain locally the strength you need for Oumuamua to hold itself together. And then also from Rosetta, there's some results from the little geological hammer on the lander, which are questioned, but potentially there's megapascal strength locally in patches. So if we compare with a comet, with Oumuamua, the composition doesn't rule out being an icy body. It looks like an icy body. The other properties don't rule this out. We can explain this as a comet. What makes it this inactive thing then when we'd expect activity? Is it because it's interstellar? Is it because it's spent all this time in interstellar space? Well, that's it. We don't really know its age to a precise level. We can say it can't really be, you know, orders of magnitude older than the Oort cloud comets, because the whole universe isn't orders of magnitude older than the solar system. There is an implication that it's relatively young from its kinematics as well. So it's probably of order similar age to our Oort cloud comets. And our Oort cloud comets also orbit outside of the heliopause. So the environment in the Oort cloud and the environment in interstellar space is basically the same. There's not really a great difference in terms of radiation environment or the processing you would expect between our own comets and an interstellar one. So why is this thing so different? And I think the largest part of this difference is actually because Oumuamua is very small. If you compare Oumuamua to a beautiful Oort cloud comet with a giant tail, this thing's Hale-Bopp, it has 50-kilometer nucleus, whereas Oumuamua was tiny, about 100 meters across, 150 meters. And so the difference, a large part of it, is probably because this is just a very small thing. It wasn't just the first interstellar object we saw, it was also one of the smallest comets we've ever actually observed. We have all this detailed spectra on it and things like this because it was a very exciting one, and therefore we could go and point VLT at it and integrate for hours to try and get a spectrum on something that was very faint. We haven't tried that on a lot of our own comets. The size comparison here is, you know, this nice plot that ESA made to show you how big 67P is by scaring the good people of London. And then the top plot is Oumuamua, and it's building size, not city size. Thing's tiny. And if it's as elongated as we think it is, then nowhere on the surface is more than 20 meters deep. And so you can easily imagine that it's actually lost a lot of its volatiles over its history just by being very small. It just doesn't have the volume to hang on to the ice in the same way that a larger comet does. And so actually, the expectation goes the other way. There probably should be a lot more Oumuamua-like comets from our own Oort cloud that are just passing us by undetected because they're very small and very faint. Oumuamua came very close to Earth. It was the first interstellar object and the first potentially hazardous interstellar object. It would count as a potentially hazardous asteroid if it was going to return. And then the last thing that came out about Oumuamua and makes it look more cometary is that comets have these non-gravitational accelerations. Because they outgas, this acts like a rocket force. This changes their orbits very considerably over each orbit. And careful measurements on Oumuamua showed that it was also accelerating. And you can't explain its acceleration in any other sensible way other than by saying this thing was accelerating like a comet. It has the same sort of non-gravitational forces. If you look at this as a plot of the non-gravitational force measurements for comets, and the black line is where Oumuamua is, it's on the high end of what we observe, but it's within the range you see for comets. And remember, this is much smaller than most comets. It's a lot easier to accelerate. And so a relatively low level of outgassing could explain this acceleration. The puzzle remains, as if it is outgassing, if it is showing this activity, why it wasn't lifting enough dust for us to detect a coma as well. Maybe it's just too small. It's not covered in the layer of regolith that larger bodies are. But it definitely looks like the thing was actually active, but didn't appear to be. I'll just briefly summarize Oumuamua as our first thing, and then we'll go on to some of the other ones. The thing with Oumuamua was that we had a very limited window. This is all based on observations we could grab with director's requests on every telescope over a couple of weeks. It looks like a comet in every way we can observe, apart from not showing obvious activity. And it could just be that this is because it's very small, and it's lost a lot of the volatiles and or doesn't have the loose dust on the surface for these volatiles to lift to form a coma. But the next interstellar objects, and now we have two more, look far more like what we would expect. These look like comets. When they were first observed, they have a fuzzy little coma and a tail. And if these had been the first interstellar objects we would have found, we would have been, yep, that is what we were thinking we would find. There's an interesting question of whether or not Oumuamua is an unusual thing, or whether there's more of them out there. 2I Borisov was the second one discovered in August 2019, with a very high eccentricity, clearly interstellar from the start, clearly active from the start. It was observable for a longer period as well, months, because the activity means that it's brighter, and actually we could go and dig in archives and find the activity started quite far from the sun. It looked quite like solar system comets in terms of dust color. It has a nucleus which is more kind of typical comet range, still small, but maybe up to 0.5 kilometer in radius. Typical comet nuclei are, up to about 1 kilometer, a handful of them, kilometer to 10 kilometers size. This is the first time we detected gas directly, so we got spectrum of it that showed CN. It's normally one of the strongest lines you pick up in a comet spectrum. And then follow-up observations as it got a bit brighter could detect other species. I'm not expecting you to see all the details on these plots, but basically it plots, and this is some of Michelle's work, looking at C2 to CN. Say hi, Michelle. She knows more about this than I do. Ask questions to her, not me, at the end of the seminar. There's plots looking at the nickel to iron ratio in comets, which is something that in the last few years we've detected these metals. It sits right in the middle of distribution there. Looking at ortho-para ratios in NH2 spectra, again, it looks just like most of the solar system ones. So it was sort of surprisingly normal after all of the excitement of Oumuamua and what is this weirdo. This thing looked like a comet and behaved like a comet, and we were like, oh, that's reassuring. It did show some oddities. So it has a relatively high carbon monoxide fraction compared with water, or compared in this case with HCN. But a little outside of the range of typical solar system objects. But there is also this weirdo solar system comet which actually had a much higher ratio. That weirdo pops up occasionally elsewhere. The other plot here is on this the green to red ratio of the forbidden oxygen lines, which is used as a proxy to say whether the activity has been driven by water or carbon dioxide and carbon monoxide. And there's this nice general trend that you see in solar system comets, apart from, again, this one weirdo. But then Borisov is quite out of the range of that. So it did have some compositional differences which were a little outside of the range. But perhaps that shouldn't be surprising, because it's not from here. Yeah, it is some sort of comet from some other solar system. It's not surprising that it has at least a little bit of difference in composition. But we didn't actually get that much more on Borisov, partially because it was detected in 2019, and in 2020 all the observatories were closed. Also, it fragmented and split up. But in general, the picture on Borisov is that this thing looked more like a typical comet with a few, little differences. Had odd polarization as well. Then we get on to our new and favorite toy. So 3I Atlas. This has been making headlines all for the last year. And 3I Atlas is interesting because this one is the first time, well, firstly, it's the first interstellar object that we've had in the JWST era. JWST is an amazingly powerful thing for comets, as we'll get into. And so we've got a lot better information on it. But also, it's bigger and brighter, and it was observable for basically a full year. Because we've seen quite far out on its way in, we've had time to coordinate and to apply for all sorts of time and get every observatory looking at it in not quite such a rushed way as we did with Oumuamua. And because it turns out to be a lot more interesting in terms of its properties, as we'll get into. So these are sort of initial results, came out in the first weekend, because people are still very excited about these things and jump on stuff fast and try and rush stuff out. The initial spectra we could get when it was just discovered, we can get this kind of red spectra. It's redder than some of the other interstellar objects and then a lot of comets. But in these early spectra, we don't get much more than that. As we keep observing it, we start detecting gases in it and can look at that. But as I said, the really exciting thing with this is we could get JWST on it. It was also followed by pretty much every other platform we could get on Earth and not on Earth. So the image here on the right is an image from the ESA JWST spacecraft on its way to Jupiter, which happened to be well placed to take an image of this around about the time of its perihelion passage, when it was behind the sun as seen from Earth, and we had a gap in the ground-based observing. And you see this beautiful ion tail structure, and there's all sorts of stuff in there to have a look at. But this is a JWST stuff. This is JWST near spec integral field unit, which is an amazingly powerful tool for comets. It's an integral field unit, so every single pixel in the image is a spectrum, or you can get an image at whatever wavelength range you like, depending on which way you think of this thing. And so you can see here's what the dust looks like, here's what the gas looks like for CO2, here's what the gas looks like for water. You can look at not just what gas species are in a coma, but where they're coming out. Is there patterns in the distribution? And the JWST results for Atlas present a lot of really interesting stuff. Firstly, in the early observations with JWST, it was targeted both before perihelion and then after again, when it got brighter. The first observations with it, when it's far out, they show really strong emissions from carbon dioxide and carbon monoxide, and some from water. So a much higher carbon dioxide to water ratio than you expect for solar system comets observed at a similar distance. Immediately tells you there's something interesting with this thing's composition. The only thing that's higher is, again, this weirdo 2016 R2. But it's higher than the general trend for solar system objects. It tells you immediately there's something different about this comet. The near-infrared spectra for comets is a really interesting place to look at them, because what you're seeing there are the main gases driving the activity coming out directly from ices in the nucleus or from ice in the coma. Whereas in the visible wavelength range, you're seeing is stuff that's being chemically processed in a coma. So we always like to be able to get into the infrared when we can, but pre-JWST, it's very difficult to observe these wavelengths. I said that also you started detecting gases. One of the interesting things with Atlas is the early high-resolution observations from the ground, with UVES and VLT, start picking up nickel emission amongst the earliest things you pick up. As I said, in the last few years, it's been realized that you get strong nickel and iron lines in a lot of comets. They've not really been looked at before. People thought, look at volatile ices. But actually, it's been realized, if you go back and look at all of these high-resolution comet spectra that people have taken over the years, that it's actually really common to see these nickel and iron features. They think that the interpretation at the moment, people think these come from these carbonyls, these nickel CO4 and iron CO4 or CO5, and that you get this these metal lines coming from those. But strangely, on this one, it had a very high amount of nickel to start with and a high nickel to iron ratio, which then kind of not got back to kind of normal ranges over the few months as it approached the sun. So some of the early results for this were like, oh, it's full of nickel and it's strange, and this also caused more misinformation. But so this is an interesting feature of it. And then the really exciting stuff comes when we start actually being able to probe isotopic ratios. So this is something that you kind of normally only do with very bright comets. And now, because this one got reasonably bright, not bright by the sort of historic standards of most of the comets you'll see on this plot, the things that were naked eye brightness and you could point a telescope on the ground at to measure these ratios. But with JWST, with Oumuamua, you can actually get at these things of sort of mediumly bright comet like 3I was. you can start measuring not just the composition in terms of what ices are there, but what the balance of the isotopes are there within those ices. So firstly, looking at deuterium to hydrogen ratio, and we see that in this one, 3I Atlas is way above any of the solar system comets. It has a higher ratio than things we find in the solar system. Factor of 10 higher than anything you see in comets. Now, the isotopic ratios we think of as being set during the formation of the comets by particularly the environment, the temperature, radiation environment, when these ices first form and solidify. We can imagine different ways to get different compositions in comets in terms of like the balance of molecules and the balance of ices. At different distances from the sun, different things will sublimate, and so the apparent composition can change. But the isotopic fraction seems to be something that's set during the formation, and so it's nice to get this as a real probe of where do these things form. And what this suggests is this thing formed cold. It formed probably a very distant part of its disk. And then things get more interesting when we start looking at carbon isotopic ratios. We can measure the C12 to C13 carbon ratio looking at CO and CO2 in the JWST data from post-perihelion, and in the CN emissions from the VLT data from the ground. And what we find are significantly higher ratios than you see in anything in a solar system in terms of the carbon ratios. And this is consistent amongst measuring it in all these different species that contain carbon. So the carbon that's going into forming this comet has to be very different from the carbon that's forming comets in our own solar system. And that's interesting because carbon ratios are actually a good chronometer. They're a good indication of time passing within the galaxy, because so the carbon 12 to 13 ratio decreases with time as you get more carbon 13 in the galaxy, and you get that through generations of star formation. And so this is giving you actually a very strong hint that when this thing formed and these ices froze, it had to be much earlier than our solar system formed. This is one of the hints that this thing is actually quite ancient object. And this is one of the most interesting things that's coming out of it. We're starting to get clues that this thing significantly predates the solar system. It's been wandering around the galaxy for maybe 10 to 12 gigayears. This agrees also with the kinematics. If you look at it, it looks like it's probably part of an old thick disk population. This thing probably formed in some low metallicity environment early in the history of the galaxy. Also got isotopic ratios in nitrogen from the same data set from the ground. Again, significantly higher than solar system comets. Again, suggests a formation, location, and an environment. So we start to get a picture put together that this thing formed somewhere in the quite outer regions of its disk around a star a very long time ago in a different chemical environment in the galaxy. You also see quite odd behavior of this thing. We're looking at the dust. So the other nice thing we can do with JWST is we can look with MIRI and we can look into the thermal infrared. And the red line in the middle is 3I Atlas. The other lines are all traces of different comets, either things that have been observed with JWST with MIRI or mostly with Spitzer in the past, so very bright comets that were bright enough for Spitzer. In all of them, you see all this structure in the mid-infrared, which is due to silicate features. This is mineralogy. These are dust grains that have got some sort of silicates in them. You've got olivines and pyroxenes that cause all the different features. You don't see those in 3I Atlas. It has this broad feature, but you're not seeing any of the peaks and the waves that are caused by the actual mineralogy, which strongly implies that it doesn't contain the sort of silicate material, the actual dirt, the dust that would have formed in a hotter environment that we see in solar system comets. One of the interesting results from Stardust mission a few years ago, that brought back a sample of dust from a cometary coma, was that it had a whole bunch of really high temperature grains in there, things that must have been formed nearer the sun, and suggests that there was a lot of stirring and turbulence in the formation of the solar system that meant that high temperature materials end up in things that formed out in icy regions. That doesn't seem to be the case with 3I Atlas. It does not seem to contain these higher temperature materials, either because they weren't there where it was forming or because it's never been heated since. It has this weird polarization signal as well. Polarization is telling you about the dust reflectance. It's telling you about size and shape and composition of the dust grains in the coma. And it has this much sort of deeper dip in the negative branch and steeper slope than all of these other comets that in the solar system that mostly follow the same sort of path. So again, still requires some explanation, but it looks connected to the fact that the dust around this thing also looks different. It's possibly one of the most ancient things we've seen, but maybe also one of the most primitive. One of the things that's got least kind of heated material in it. The strong possibility that it's the first time it's ever come past a star, and maybe it never actually got very close to its host star as well. This is some speculation to think about. But yeah, 3I Atlas is an evolving story. There's more papers every single week, and there's more results to come out on this thing yet. But it was brighter and visible for longer than the previous interstellar objects, and it's the first one in the JWST era, which is this whole amazing window on comet science. The moment we're lacking enough observations of other comets with JWST, and we need to do more of those to really understand the context of this thing. But the emerging picture is that this is probably the oldest thing, solid thing, that we've ever seen. It predates the solar system by a long time. So apart from being able to see very old stars, this is the oldest solid thing we've ever encountered. It probably formed kind of in the peak of Milky Way star formation. You're looking at, if you think to extragalactic people, talk about cosmic noon and peaks of star formation. This is from then, it's just from here. This is a redshift 0 cosmic noon thing. Is it the first time it ever got close to a star? Quite possibly. And the dynamics of these things mean that they rarely encounter stars as they go wandering around the galaxy. It could have spent 12 giga-years wandering around the galaxy and never actually come particularly close to a star. Douglas Adams' space is big, really big. So you can have these rocks wandering around and never actually getting heated all that much. And maybe if it formed in the very outer regions of its own star, it actually escaped from the outer regions without getting particularly heated before it did. That is wild speculation that we can have some fun with. But these things are interesting, not just because it's a really interesting object and it's a weird comet, but we're getting to the point where we can start to use these things to tell us something about the history of planet formation, not just in our solar system, but across galactic history. We can say planetary systems were forming back at this era because there's something solid that came out of a system that must have been forming then. As we find some more of these, we can start putting together what is common and what is unusual. And there'll be a lot more to come on this one. Okay, I wanted to talk a little bit, apart from what we know about the ones we've seen so far, about what we expect to see soon, what is coming next. I don't need to introduce the Vera Rubin Observatory to many people here, but I will anyway. It's a really big survey that's just starting with a really big telescope in Chile. It's going to find lots of everything, is the very simple summary. For solar system, it's going to be amazing. Essentially, we expect order of magnitude increases in pretty much every population of solar system type of body, except planets, probably. How many interstellar objects is it going to find? So that is a big, interesting question. To find out how many interstellar objects you're going to find with this big new survey, we have to think about, well, what's the size distribution of these things? What's the typical size? Are they all Oumuamua size? Is Atlas more typical? We need to think about how they distributed around the galaxy and how, are they just a uniform that we run into them? Are they spread in different ways? Or what's if they're uniformly spread, what's the average space density? How many of these things per parsec are there around? We need to think a bit about their activity. Do they behave like Oumuamua, typically, or is that the weirdo? Or do they, where would their activity start? Would they start being active 10 AU from the sun, 50 AU from the sun? When do they start to grow the coma and tails? Because it makes them much brighter and much more easy to pick up in a survey. than the same size nucleus if it's inactive, and just reflecting sunlight from the solid surface. And then finally, you need to think about what does your survey look like, area it covers, how deep does it go, etc. And so what can we do about this? Well, size distribution, as I said, we now know 3 objects, so that's great. We can do a size distribution with that. If you're really optimistic, you can kind of extrapolate all the way back to, we know that there's kind of interstellar dust. We pick that up. I have seen plots that try to do that go and connect one to the other. I've been co-author on some things that have attempted to do so, and then there's a big kind of question mark in between, because microns all the way out to Oumuamua at 100 meters is a little gap, but are these things just a distribution all the way from interstellar dust to big things, or are these very different? But we know a few objects now. We can constrain this better than when we started doing this with one object or with no objects in the first predictions. We have nice models that say where these things go. How do I pronounce it? Aututahi. Thank you. Ask the Kiwi. Aututahi Oxford model is this nice distribution of where should you find these things, considering galactic dynamics and considering populations of stars in different eras and things like this. And so you can have a model that actually takes into account all of this galactic history of star formation and therefore planet formation, and what does it predict for planets, for interstellar objects. The activity pattern is definitely a big unknown. Is Oumuamua typical or weird? Is it that the really small ones we expect to be inactive, or is it that some are just not so rich in volatiles to start with because they come from an inner part of their disk rather than an outer part? And then finally, how do you actually take account of your survey? Well, there are tools to do this. There's one called SORCA, which is designed particularly with LSST in mind in solar system populations. You can fit in any population of orbits you want and sizes, and it will tell you how many LSST should find. And the really important point with all that is that you can use this not only to make predictions, which, current put-in best guess numbers on these are a few to a few tens of objects over the course of an LSST survey, but more importantly, you can take all of this, and then when you have got an LSST survey and you found however many, and they look like, active, inactive, whatever, you can start constraining these inputs a bit more. You can use the same survey simulators to debias your survey and work back to what we think the underlying population is. And because this underlying population depends on the history of planet formation in the galaxy, you can start to get some constraints on that very big topic from the handful of little things that pass close by us. And so we have a few key questions for LSST that we really want to look at with interstellar objects. The first and most obvious is just how many of these things are out there. We'll get this from how many we discover. If after 10 years of LSST we've still only found a handful of them, they're intrinsically rare, and we have to re-evaluate our numbers. If we find 10 every single year, we're going to be less crazy excited and grab every telescope we can get for by the time we get to 10i or 12i, people are going to be, do you really need to get spectra of everyone? Yes, we do, is the short answer. But, if we'll get into the numbers game a bit more. I mean, still, 10 objects is it's not exactly the most of LSST science where tens of thousands of sample is a kind of minimum. But yeah, one of the key questions that we'll get with LSST data is where the activity starts on these as well. It's a very sensitive telescope. If these things are actually active when they first notice the sun's heat at 30 AU, we'll pick them up out there. If they're only really turning on as they're getting closer in, because activity is being driven by volatiles that only see the sun later, or because they've got this thick thermal blanket like I talked about with Oumuamua, and that has to be gotten through before activity starts, then we'll see evidence for that. I think a really interesting question is whether or not Oumuamua is unusual. Not only an interstellar object population, but if that is because it's if its size, if it's just because very small comets lose their volatiles, and you should see a whole population of not interstellar objects, of Oort cloud comet-like orbits but that look like Oumuamua, things that are small and low activity, and we've just not detected yet because they're very faint. And as we get a more powerful survey and we get a larger sample of space that we're sensitive to these things in, do we start seeing a population of those and realize that Oumuamua is not so unusual? It's just that we were lucky that it came very close to Earth, and that we have similar things in our own solar system. And then the really interesting questions when we start to get a larger number of these and we start to compare with models of, like, do we see significant differences between something very ancient like 3i Atlas and things that look like they're younger, that they've come from more recent star systems? Do we get big differences with different ages from things or from different bits of the galaxy and different parent systems? And can we start to really map these differences across the galaxy and across time? And then finally, I'd like to talk a bit about the idea of, like, well, can we get spacecraft to one? Because, you know, these observations are all great, but how cool would it be to go and have a spacecraft fly past the most ancient thing ever? And the short answer is we probably could. So to get a spacecraft to something that you only see fleetingly pass through the solar system, what you need to do is react quicker than the timescales you think of for space missions. Typically to get a space mission designed and approved and built and launched, decades of time. Yeah? And that's, you're not going to have a chance to do that with an interstellar object that you might see for maybe a year, maybe a couple of years if you're lucky with LSST and you detect it far out. So how do you do such a thing? Well, the questions with interstellar objects is very similar actually to if you want to send a spacecraft to a comet coming from our own Oort cloud. The problems are the same. We generally detect them only months to a year before they pass the sun, and then they're gone, and they might be back in 30,000 years, but that's not really helpful. And so we have a mission that is under construction right now called Comet Interceptor, with this European Space Agency mission that is designed to go and see one of these long period comets. And it's designed to do this by building a spacecraft, launching into space, and then finding the target, which is a fun and exciting engineering challenge that we're amazed that ESA let us do. In this case, what we do is we launch to a parking orbit around the L2, Sun-Earth L2 Lagrange point. This is where JWST is parked, where Gaia is, as well. All these good place to put observatories. You can kind of hang out there with minimal fuel usage, so a good place to park in space. And the advantage of being in space and having a spacecraft built already is you can actually react much quicker when you find a comet coming that you like the look of. And so the general sketch of how Comet Interceptor is going to work: we launch and put ourselves in this halo orbit around the L2 point, where we hang out for a couple of years. Meanwhile, scan the skies with LSST and NeoSurveyor and whatever else, until we find a comet that we like the look of, far out in the solar system on its way in. And we predict where that thing's going, and we see this is crossing the ecliptic somewhere near Earth's orbit. Comet Interceptor can't get that far. We can't go out and meet the comet out by Jupiter or anything like this, but it can get to anywhere around Earth's orbit away from Earth. So if we find one that's coming near to Earth's orbit but not necessarily that close to the planet, we can then go and spot it and predict where it's going to cross. And then we fire the rockets and we head off to meet it and set off the intercept point while we keep an eye on the comet from the ground, and we watch its activity increase and so on. And then we have this fast flyby encounter as the comet crosses the ecliptic plane, where we go shooting past the comet and we get a whole bunch of data inside of 24 hours. Most of the previous comet missions, this is going back to the earliest comet missions, this is very similar to what Giotto did with Halley in the 80s. You get all the data in a very quick passage. It's only Rosetta that's gone into orbit around a comet, and that's not really feasible with one of these things. But what we can do is we can push forward, not just going to a new sort of comet and a new sort of target. Comet Interceptor is also the first time we'll take multi-spacecraft mission to a comet. So we have our main spacecraft, and then we have two probes that we release as we get to the comet, which is nice scientifically because we can get multi-point measurements within a coma. You can tell whether or not the measuring different composition at this point and this point is because of some inherent difference in the different side of the comet or because of some time varying thing. You couldn't even do this with Rosetta. If you measured composition on one side and then you measured composition on the other side, well, it took you 3 days to fly around to the other side. So you don't know if the comet changed in the meantime or it's intrinsic. But it's also, apart from getting this 3D picture, a very useful thing to do for a fast flyby comet mission, because you're going to shoot past this thing at up to 70 kilometers per second in a cloud full of dust coming off this comet. Each one of these dust grains is relative velocity to you is essentially rifle bullet. Spacecraft not very keen on flying through hails of rifle bullets. And so the main spacecraft has a relatively large distance flyby, about 1,000 kilometers, which will still be within the coma, but within a reasonably safe distance approach. While the smallest probes that get sent deeper into the coma, where they are designed to be expendable, they will get close-up measurements and they will last for as long as they last. This is what spacecraft looks like. We can go into more details on this if you want, but it's a collection of various instruments. It has infrared cameras, high-resolution visible camera, has an in-situ mass spectrometer to measure composition actually of what it's sniffing in terms of the gas, has a whole package of sensors to measure magnetic fields and to look at dust impact detections and to look at charged and neutral particles. And then the individual probes also have various cameras, polarimeter to look at the reflectance properties of dust from inside the coma, and also, you know, in situ sensors that build up this 3-point picture as we fly through. This is currently under construction. In fact, the first instruments are already being delivered this summer. The rest are due for delivery by the end of the summer. And so there are some very nervous hardware building people around, frantically soldering as we speak. But this is on schedule, and it should launch late 28, early 29. This is actual hardware being built. And then it's up to a 6-year mission, so we're talking about kind of mid-2030s for a comet flyby, to be confirmed once we actually have a comet. Okay. Can we do an interstellar object with comet interceptor? This is always the big question. The short answer, probably not. But it has always been sold as one of the, you know, it's possible. It's kind of unlikely, but it's possible as an interesting science case. The fact we're already waiting in space means that if we spot one that's coming to the right area with enough warning time, it's possible. And there's a fairly unanimous viewpoint within the science team that if we see one we could get to, we will. But the difference with an interstellar object compared with a solar system comet is these things tend to be going really quite fast relative to us and the sun. The warning time, even with LSST, is likely to be relatively short. And they don't seem to be so amazingly common that they're all over the place and that there's a good chance we'll find one. So we'd have to be lucky. We'd have to find one that's coming, you know, reasonably close to Earth, and we could reach with a short cruise with relatively little warning time. So the interstellar object case is not driving the mission design. It's not driving the development of science plans. It's something that all of us have in the back of our mind of like, it would be great if we could, but realistically, it's reasonably unlikely. And Comet Interceptor is going to do what it's designed to do, which is to visit one of our own Oort cloud comets, which is something we've never seen before and is super exciting scientifically in itself. But I'm here talking about interstellar objects. We all agree these are super exciting things. What would it require to get to one? So some of us have given this some thought. Essentially, I think you could reasonably do this with a kind of stripped down Comet Interceptor. You could do this without the separate probes, for example. You could do this with limiting your payload to really only sort of cameras and spectroscope and remote sensing. I'd argue you'd probably still want the mass spectrometer because it would be cool to measure in situ the composition of something that's come from another star system and really get, you know, detailed composition that you can only get with an in situ measurement. But you can imagine a kind of a stripped down version. But essentially what you probably need more than that is you need to have its own dedicated launch and a more mass budget dedicated to big fuel tanks and bigger delta V. Because the real limit we have with Comet Interceptor, this is launching as a secondary payload. It's a small class of mission. it is limited on how much fuel it's got and therefore how far it can get and how quickly it can get there. Whereas if you built a version of it that was basically designed as a speed machine that was big fuel tanks and designed to go, that's what you probably need to get an interstellar object. And that feels like that will be a realistic thing to talk about for a medium-class size mission in the next decade or so. What we're lacking, but what we will have with LSST, is the kind of statistics to really say this is how long you're going to need to wait for to realistically have a chance to get one. This is how common these things really are. This is how far and wide you need to cast the net to have a good shot of catching one. But that's the sort of information we will have in the the next decade. And so this feels like a realistic prospect in the not too distant future. But I think it'd be hard to propose it now because we're still, there are big question marks still in the population size. Okay, so I'll finish here with a summary of the points. So the cool thing about interstellar objects is that there's really an opportunity to look at the things that build exoplanets. We like comets and asteroids because they're the building blocks of our solar system. Here we get to extend that to what are the building blocks of planets more generally. What is the history of planet formation across the galaxy? Oumuamua was this very weird thing, something unlike any comet asteroid we know. It doesn't mean it's an alien spaceship. You can explain it all as things that look a bit like comets or asteroids, but it has some odd properties, most of which are probably to do with the fact it's very small. Borisov was surprisingly normal, a few odd bits, but nothing too unusual, whereas Atlas is turning out to be really exciting and interesting, and as I said, probably the most ancient solid object that humanity's ever encountered. And has potential to tell us a lot about not just planet formation, but history of planet formation across galactic history timescales. And then Comet Interceptor is this exciting thing that is launching soon, and we're going to go and explore some long period comet from our own Oort cloud and compare those with what things look like for interstellar objects. If we're very, very lucky, we could go and see an ISO, but probably not. And that's the next mission to think about beyond that. But first, watch this space for a Comet Interceptor. And with that, I'll stop and happy to take any questions.
Thank you very much. I will open the floor to questions, particularly from students and postdocs to start.
Hello. Maybe I just didn't catch it, but this isotope ratio you can use to sort of infer the age. But then you also mentioned this like carbon monoxide dioxide versus water ratio, and that this was very high for the Borisov and Atlas, and that there's also a trend for the solar system. What sets it? Is it just like the temperature
So the carbon dioxide, carbon monoxide to water ratio, this is probably controlled more by the temperature that the body's feeling now and what gases are coming out now. And so this is why we see these trends with distance from the sun when we observe solar system objects, that when it's further from the sun, it's too cold for water ice to sublimate, but activity is more driven by carbon monoxide or carbon dioxide because they're more volatile. They'll sublimate at lower temperatures. And so we think that we see this trend with distance for this ratio, this green thread ratio that traces which molecule's driving it, mostly driven in solar system objects by that what it's feeling now, rather than a difference in composition. So the same comet, if you measure it at multiple different distances, will appear different depending on distances. Borisov was odd in that it didn't fit on this trend, it was kind of above this. So at the same distance, it was having a different ratio. But maybe that's not so surprising because, within our solar system, if comets formed at sort of similar distance ranges where the giant planets were forming, they probably have a lot of them similar kind of ratios. Whereas, a comet from another star system, maybe it's where it's formed and where it's got ejected from depends more on where the giant planets were forming in its system than necessarily where big differences. Whereas the isotopic ratio is a bit different, so that's ratios between the actual molecules and what you're seeing. Whereas the isotopic ratios, we see those tend a bit more to depend on, these are locked in when the ice is formed, and they don't change so much as depending on the heating and when it released. They were depending more on what the balance was between the different ratios of material when the ice is first froze. So that tells you a bit more about formation location rather than where you're seeing the activity now.
Hello, thanks. Here in the solar system, it's quite common to find chondrites with aluminium and inclusions. And you mentioned that 3i Atlas is supposed to be ancient and could provide information about fun information in early times. So do you expect these kind of comets to have aluminium inclusions?
Excellent question. And unless we got kind of a sample from one, it'd be difficult to tell, because the CAIs is something you see in meteoritic samples, but they're not something that we detect remotely. And you take a spectrum of an asteroid, and you get this very vague kind of C-type, which is a mix of a whole bunch of mineralogies, but it's not telling you about, you know, really microscopic things, the CAIs. And so we see those in meteorites. We know they're there because we can get these in a lab and look at the microscope. It'd be a very interesting question that if we got a meteorite, you know, a genuinely interstellar meteorite that had a different formation history, whether you'd see them. I guess you would sort of expect to see them. I guess the idea is that these things formed, you know, early in the formation of the solar system or pre-solar system and were incorporated into solid material, and there's no reason why they shouldn't form elsewhere as well. But maybe you would have different proportions of them, and maybe again you would get different age markers because, you know, using them as a chronometer, because things could be at different ages. But yeah, it's not something we could do with remote observation or even really with a spacecraft. This is, you really need a sample and a microscopic sample to look at these things.
Thank you for the talk. What is an estimated number of objects like 3i Atlas? I mean, we're very lucky that in 2 years after JWST launch, we found that object, and it was the first flyby through the star, as you said. And what is the estimated number of such objects?
So there are a few estimates on sort of space density of it, based on trying to, you know, debias Atlas survey and say how many should you have found and so on. I'm trying to remember a number off the top of my head for what this is. This number, you know, you get some number per, you know, cubic parsec or whatever. It's not crazy that we found these things. I mean, we found 3 now. We found, you know, the first one we got very lucky. It passed by very close to Earth, which is why we picked up such a low activity thing. But actually, Oumuamua was discovered a couple of months after a paper was published looking at the Pan-STARRS survey up to this point and doing statistics and saying, well, you know, if we look at the sensitivity survey and based on this model of how many interstellar objects should be out there, based on, you know, 0 detections, Pan-STARRS should probably be about, well, 1 detection by now. And then 2 months later, 1 detection. So those people were very smug. But they didn't predict that it would look anything like Oumuamua. So it is just a, you know, it's a numbers game with these things. And now the surveys are getting a bit more sensitive. So we found a few more than we found with Pan-STARRS. We expect the rate to go up again with LSST. I think the Atlas folk were very happy that they found one, you know, weeks before LSST was going to do its big first light announcement and completely change the game for finding stuff. And Atlas found one with a 50-centimeter telescope instead. But yeah, again, if you look at the statistics and the underlying models, we're finding them at kind of the rate you would expect, we think, based on, you know, what we think now the population size is and the sensitivity of these telescopes. So it's not so much that it's like the first one that would possibly have been observable with JWST. If we had JWST already in 2019, we'd have pointed at Borisov and we would have got really cool results there and probably know more about Borisov than we do. It's just that it was the first one we had the opportunity to do with JWST.
Thanks for this very nice overview of these interstellar interlopers. I have a question about the third one, Atlas, and your inference that the thing is very old and has very pristine chemistry. And in this context, I'm wondering about surface contamination. If this thing cruises through the Milky Way for, let's say, 10 gigayears, or make it 8 gigayears or something like this, what are the chances that it accretes material on its surface and what we see in the outgassing now and in the spectrum is just the accreted material and not the original one from its own solar system?
So I don't know about accreting material. I guess potentially it's going to pass through some giant molecular clouds. It's going to have some alterations to it, but certainly would expect that the outer layers would be irradiated and just from cosmic ray impacts, and this would change some of the outer layers. But we also know that, you know, it has passed the sun and it's had a level of activity that suggests it's lost meters of its surface now from the erosion that it's had. And then the JWST results are looking at the